Previously, we have discussed what exactly numerical methods do. We have seen that from an example, and then we have tried to generalize the idea of what we have learned from that example. I have also stated that in this course we will primarily talk about the methods and not so much about the applications here. However, we have to understand that numerical methods are always closely connected with applications. And that is where, in this lecture, we'll talk about that how exactly physical problems and numerical methods are connected. And we'll have this lecture as well as the next lecture. We'll take up an example and try to understand that. So numerical methods, what it does, as we have seen before, that it solves the usual problem of algebra or calculus using simple, repetitive arithmetic operations. However, the problems that are solved using numerical methods, they are most of the time, or I should say always, they come from practical engineering application problems. So let us discuss one small problem here. So let us say that we are designing a parachute that will supply certain essential payload to a disaster affected area. For example, in an area in Himalaya where we want to supply food or medicine. Sometimes we use parachute and we do an airdrop. We cannot directly drop the payload because then it will be destroyed through impact. Now, if we want to design such a system, it will be a very complex process and we will not go through that complex process here. That is not the purpose of this course. But let us take up a small aspect of that. Let us say that we know the height of release, where I'll release it from the aircraft, and we know the load, what is the mass of the payload. Knowing this, we want to calculate at least the speed at which the payload hits the ground. We have to understand that if it hits the ground really hard, then all the supplies that are coming in this payload, they will be destroyed. So the speed is a key component here in this design. Of course, this design has many important components, but the speed of this payload when it hits the ground is one of those important components. And we want to calculate that, or do we want to find that, not necessarily calculate. So how do I find that? Usually there are two ways to find this velocity at the ground or any other quantities that you think that may be necessary for such design. There are two ways to get them. Number one is experimental. So you actually do it and measure how the payload is hitting the ground, what is the velocity of payload. Then for that, of course, you actually need a parachute and a payload. This will give you a very good result. You can do it that way. The second option is that without going through this experiment, you do it using pen and paper, or we may say that in a digital computer if you require numerical work. So the second aspect is mathematical modeling. So a calculation of this speed at ground. Experiment, when you do it, it will be expensive and it will be time consuming as well. It will take a lot of effort and a lot of money to make one of this thing. Even if you make it a small model, you have to create a small model, you have to pay money and give time to make it. And then you have to actually do the experiment. In some of the experiments, your payload will be destroyed. So overall, it's a lot of effort, a lot of money and a lot of time. And sometimes this kind of experiments may not be ethically correct. So for instance, if your payload is a military supply, it may contain certain ammunition or certain chemical which are harmful. Then this kind of experiments are not something that we do very easily. So they could be ethically questionable. So in all such cases, we get a cheaper and quicker solution through mathematical modeling. And what is mathematical modeling? So in mathematical modeling, what we do is that we take up a physical phenomena or a physical problem and we express that physical problem in terms of mathematical equations. These equations are usually derived from conservation principles, that means conservation of mass, momentum, and energy, or it can come from lots of data, that is the data-driven model which we'll talk later, and most of the time it will have conservation equation as well as some data will be needed here. This is how we can create a mathematical model of a physical phenomena. Once we create the model, we can forget about the physical phenomena and we can try to solve this model, and that part we call simulation. In simulation, we solve the model equations. Together, this mathematical model and its simulation, this is in the heart of engineering, this is in the heart of design, and this is closely connected to numerical methods because simulation will often require numerical methods. May not be always, but many times, most of the times it will require numerical methods. So what we'll do now, we'll see now this problem if we simulate without using numerical methods, how far we can go. Will it be realistic? And to make it realistic, what we need to do, we'll discuss that here in this problem. So let us say that in this present case, that one parachute will drop a mass of m. So that is my mass of payload. And it will release from a height h, and the downward speed of payload, which of course will change in time, but that speed is u. We are interested to find the speed at which the payload reaches the ground and symbolize that as u naught. So first, of course, we have to create a model. So how do you make the model? Of course, it will come from the momentum balance or momentum conservation equation, which is essentially the Newton's second law, which is the force balance. So what is the force balance here? The simplest way of balancing the force is that this force, that is mass into acceleration, m multiplied by du dt, will be given by this mg. So the payload is falling due to the action of gravity. That is why this mg force is coming. You can see that this is a differential equation. This is not an algebraic equation. So solution of differential equation will require, in this case, this is a time-dependent differential equation dt. So it will require an initial condition. And we take that initial condition, that is u at t equals 0 equals 0. So when I am dropping it, I am dropping with 0 speed. We can solve this differential equation with this initial condition. It will give us u as a function of time. Of course, we know the release height, that is h. H will be integration between 0 to t naught, u dt. U is a function of time. Once we get the u as a function of time by solving this differential equation, we should be able to integrate it. Once we integrate it, you can see that this t naught is unknown. So from this, we should be able to calculate t naught, because in this particular equation, you see only t naught is unknown, h is known, u is known as a function of t from the solution of differential equations. So from this equation h equals integral u dt, we should be able to calculate this t naught, and t naught is the time required for the payload to hit the ground. Now that we have calculated this t naught, don't forget the goal of all this exercise. We want to know the speed of payload at the time when it hits the ground. So we have calculated that it takes time t0 for the payload to hit the ground, and we already know u, that is the speed of the payload, as a function of t. Therefore, the speed of the payload at ground level is u0, which is u at t equals t0. T0 we have calculated from this integral. So this completes the picture. So this is our model now. So all these equations together makes our model. So we have one differential equation with initial condition, then one integration, and then u0 equals u t at t0. So this is all this equation makes our model. Once we have the model, we have to make a simulation, means we have to solve this model. Now m du dt equals mg. The solution is very easy for this. With u initial condition as 0, u is equal to gt. If you don't remember it, you can actually solve it as gt plus c and then use the initial condition, so the constant will be 0. So u is gt. Then we can come to this integral, and this integral will give us h0 to t0. gt is my u dt, which is half g t0 square. Now we know h, so t0 is root over twice h by g, and which gives us u0 equals ut equals t0, which is equal to root over 2gh, because this is g, multiplied by root over 2h by g, which is 2gh. And this is our simulation results. So you may be wondering that it's so simple. We already know it. What is the point of making all this fuss here? And we'll go deeper into it. And we have seen the model, we have seen the simulation. The good thing about it that this simulation relies completely on analytical methods, and the numerical methods, or whatever you are going to learn in this course, they are not really useful in this particular simulation. This is very simple, and analytical method is good enough for that. But is this simulation or is this model really a good model for the problem that we are solving? This is something that we have to discuss, and we'll come to that point subsequently. Now to summarize, what we have learned is that first there is a model, and what a model does is that it takes up a physical problem and express the physical problem in terms of mathematical equations. And then comes the simulation. What the simulation does is that it solves these mathematical equations in the model. We can clearly see that modeling brings a sense of abstraction, which is extremely important in engineering practice. That this abstraction will make it general. So model developed from one problem may be used in another because of this abstraction. For your exercise, you write an example of mathematical model that you have studied. Maybe in some other courses, you describe that model here. So that's all for this lecture. Thank you, and I'll see you in next class.